we learned what is the meaning of a complex number, and after that we looked into what is z, z bar, the conjugate, etc. Right? So I just want to check for more properties of conjugate. Can we write something in terms of addition, subtraction, multiplication, so on? Probably we have looked into a couple of them, while just by figuring out what is a conjugate. For example, we had seen that if I add the number, that is a complex number, and its conjugate, I'm going to get the real part. This is very logical. Suppose, let me take the general, say, complex number as a plus ib. Then what is the conjugate? Conjugate is nothing but I have to change the sign of the I term, right, which is b. So it will be a minus ib. Can you see if I add these two and divide by 2, this is nothing but the real part of the complex number, or in other words, a. Correct. Similarly, if I subtract uh, and divide, so I'll get 2ib. So if I divide this by 2i, right? So get a mistake. So if I subtract, I'm going to get 2ib. Okay. If I divide by 2i, I'm going to get b, which is nothing but the imaginary part. Correct. And I think we have seen one more property, which is z into z bar, which is also very important. Okay. So what happens when we multiply a plus ib and a minus ib? We can simply use a square minus b square. So it is a square minus, say, ib whole square, which is nothing but a square minus I square b square. I square is nothing but minus 1, therefore we get a square plus b square. Now we know the modulus of a complex number or magnitude is nothing but root of a square plus b square. So this will be nothing but modulus z square. That means you're saying that if I multiply these two complex numbers, I'm always going to get a real number. That is the square of the magnitude, right? This is an important property. So similarly, I just wanted to figure out, so suppose what will happen if I add two complex numbers? Like if I add two complex numbers, let us take z1 as a1 plus ib1 and z2 as a2 plus ib2. We have already seen addition. What I want to do is add these two complex numbers, then find a conjugate. Okay. So is there some relation with this, with z1 bar and z2 bar? That's what we're trying to figure out. If I add them, let's look at it. So a1 plus ib1 plus a2 plus ib2. So the conjugate of the entire thing, right? So I'll just combine the real parts. So a1 plus a2 plus I into b1 plus b2. The conjugate of the entire thing, this is nothing but a1 plus a2 minus I into b1 plus b2. Right? So is this somewhat related to z1 bar and z2 bar? Okay. So the pretty obvious guess would be z1 plus z2. So that's what we're going to try, the conjugate of those. So z1 bar is what? a1 plus, sorry. Z1 bar would be a1 minus ib1 and z2 bar would be a2 minus ib. Right? So this is nothing but you can see the combining terms, which is a1 and a2, which is a1 plus a2, and the imaginary part similarly is minus I into b1 plus b2. You can see it's equal to z1 plus z2 whole power, right? Or in other words, we can say that z1 plus z2, the conjugate of this is equal to z1 plus z2, right? So instead of multiplying or adding and then figuring out what is the conjugate, if you directly know the conjugate, probably you can simply add them. So this is a simple usage of property. This is pretty obvious. So it's easier. But when we go to multiplication, you can see how we can use that. Yet, similarly, if you want to check for z1 minus z2, right? Let us do it here itself. So a1 plus ib1 minus A2 minus IB2. So conjugate of A1 minus I2 minus, sorry, let me keep it as plus so that there's no confusion. B1 minus conjugate of this is nothing but say A1 minus A2 minus I into B1 minus B2. Again, we can directly take the conjugate and try. So if I directly take the conjugate, Z1 minus Z2, right? So this is A1 minus IB1, negative of A2 minus IB. Correct. You can see that we're going to get the same answer. The A1 minus A2 minus I into B1 minus B2. Right? So you can write this as the other properties. Even if I subtract the two complex numbers and then take out the conjugate, it's equal to the difference of the conjugates itself. Okay. So this was pretty easy to see. What if I multiply these numbers? Instead of simply adding them, what happens if I multiply? So what I'm interested is in Z1 bar into Z2. We have seen Z and Z conjugate. Okay, that gives us modulus of Z square. Okay. Now what if I take two conjugates and multiply? Is it somehow related to the product of the conjugates? Okay, it's better if I directly take, say, first Z1 into Z2. First we'll multiply, then figure out the conjugate. So let us look at. So this is A1 plus IB1 into A2 plus IB2. After that, we'll try to take the conjugate of this. Okay. So what is the product? Product is A1, A2. I'll directly write instead of writing most steps, right? So minus B1, B2, because I square is nothing but minus 1. Then the imaginary part, I. I is with A2, B1 plus, again, there is one more I, which is A1, B2, right? So I have to take the conjugate of this. Okay. So what would be the conjugate? So the real part remains as it is, and the imaginary part we have a change in sign. A1, okay. Now let's try to multiply Z1 bar into Z2. Let's see if they're the same. Now it's A1 minus IB1 into A2 minus IB2, right? We'll just multiply directly again. A1, A2. Now minus IB1 and minus IB2, those minus will get cancelled, but I square is anyways there. So I'm still going to get minus B1 into B2. Okay. I terms. Now I term is already negative, so I'll keep minus I outside. Or let me write it down, then I'll combine. So minus B1 into A2, which is A2 B1, again minus I into A1 B2. Now you can see again, this is nothing but A1 A2 minus B1 B2 minus I if you take it as common, so it's A2 B1 plus A1 B2. You can see that these two are equal. So again, you can extend this property and say that Z1 into Z2 conjugate should be same as Z1 bar into Z2. Okay. Now I can guess, we're again going to try for division. In this case, I don't think it looks like it is going to be true, but we can try and figure out, right? So Z1 by Z2 will do. Then find the conjugate of the whole, okay? The entire part. It's not only Z1 bar. So what is Z1 by Z2? It's A1 plus IB1 divided by A2 plus IB2, right? So we know whenever there's division, what we do is multiply with the conjugate again. So we have to multiply with the conjugate of the denominator, A2 minus IB2. Numerator would be A2 minus IB2. So denominator is a constant, right? So I'll simply write it as K. Okay, let us leave it as it is. Let us write it as A2 square plus B2 square. It's not that big that I have to substitute with K. Okay, numerator, what happens? A1 into A2 Fine. B1 into B2 with a negative sign. So there's already one negative and I square. So it will be positive. So B1 into B2. Fine. I terms. So if I combine the I terms plus I into A to B1 minus I into say A1 B2. If I take I common, what do you get? If I want, I can keep the constant separately. It's A1 A2 plus B1 B2 divided by say A2 square plus B2 square plus I into, again, I'm just separating the denominator, nothing much, right? So A2 square plus B2 square. Numerator is A2 B1 minus A1 B2. So this is just the division, that is Z1 by Z2. Now you have to find the conjugate of this. The conjugate of this would be nothing but the sign would change, right? We have already separated in the form of A plus IB, somewhat there. So only the sign of I will change, right? So simply write the same. Okay, this was conjugate of everything. So just write it here. So there's no confusion. So it would be say A1 A2 plus B1 B2 by A2 square plus B2 square minus I into the same thing. So let me just write it down. A2 B1 minus A1 B2. Okay. Now what are we going to try? We'll try writing Z1 bar divided by Z2 bar and see if it's equal to the thing we got, right? So Z1 bar is nothing but A1 minus IB1 and Z2 bar is A2 minus IB2. Okay. Multiply with the conjugate. So A2 plus IB2. Can you see that denominator is always already matching, right? Because you're multiplying with the conjugate. It's almost becoming the same thing. Numerator A2 plus IB2. So you have to multiply both numerator and denominator with the conjugate. Now denominator will be A2 square plus B2 square. Same logic. A plus B into A minus B, right? Numerator A1 A2. Again, this minus into minus, so it will be plus B1 B2. So you can see already the real part is already matching. Let's look at the imaginary part right now. It will be minus I B1 A2 plus A1, sorry, I A1 B2. Now, if I take minus I common, you can see that both the terms are exactly the same. Correct? By A2 square plus B2 square minus I into, again, denominator is A2 square plus B2 square, A2 B1 minus A1 B2. Okay. So we have looked at all the four results, and all the four results actually they were equal. So whenever I took the conjugate after performing the equation, right? Whatever it was, addition, multiplication, division, right? Then I took the conjugate separately and did it. So when I performed the operation and then took the conjugate, that was same as when we took the conjugate first and performed the operation. So it doesn't matter which operation it was, addition, subtraction, multiplication, or division, still the result holds true for all the four cases. So let us look at this problem. Z is equal to 1 plus I by 1 minus I. And we have to find the conjugate of this. Okay. Now let us look at the new properties which we have learned. We can find the conjugate without using any of the properties. What we do, we try to simplify this, get it in the form of A plus IB, right? Then we write as A minus IB and stop it. But just because we know how to find the conjugate, so we can write Z bar as 1 plus I divided by 1 minus I, whole conjugate, right? Now we know the property. What is it? Z1 by Z2 whole conjugate is nothing but Z1 conjugate by Z2 conjugate. Z1 bar by Z2 bar. Then we use it here. So this will be nothing but 1 plus I bar by 1 minus I bar. Can you see it's very easy right now? 1 plus I bar is 1 minus I, and 1 minus I is nothing but 1 plus I. So this would be an option. Just to make it clear, how else would you have solved? Now it depends on what the option in your test paper or any quiz paper is. Okay, because the options might be something different. Look at this. If you didn't know these properties of conjugates, right, what would you have done? You would have first tried to rationalize the denominator. So let us do that. 1 plus I into 1 plus I. Now, denominator is nothing but 1 plus 1. Numerator is 1 plus I whole square, which is 1 plus I square plus 2I, which is nothing but 1 minus 1 plus 2I divided by 2, which is nothing but I. Can you see the actual complex number what we are talking about is nothing but I. So this is I. So when we talk about Z bar is nothing but minus I. Now you may say, I got minus I here and this here. Are they same or different? Now let us try to simplify the same here. Let us try to simplify it here. So again, how to simplify? We multiply with a conjugate 1 minus I into 1 minus I. Fine. This is nothing but denominator is 1 plus 1. Numerator is 1 plus I square minus 2I, which is nothing but 1 minus 1 minus 2I by 2, which is nothing but minus I. Can you see both of the answers are the same? Now it again depends on what options are given or which form it is given, correct? So if it was given in this form and you would have used this method, I don't think you would have gone back to checking whether it is minus I. Okay. So it all depends on which form you want to get it. If it's again in the form of Z1 by Z2, it's very easier to use this, the properties. Okay. After that, you can always simplify if you want it in another form. Okay. So it's always better to use these properties. So suppose say A plus IB by C plus ID. Suppose this is equal to X plus IY. Okay. If this is equal to, prove that A minus IB by C minus ID is equal to X minus IY. And two subparts in proving. And say A square plus B square by C square plus D square is equal to X square plus Y square. Now, because we already know the property is much easier, right? So, what is this? Or everything is a complex number, right? Z1 by Z2 in that form. So, look at it. So, A plus IB, C plus ID. You can do in the long form, that is, you can rationalize and again complete the problem. But let us directly use the properties. Simply by taking the conjugate on both sides, what do you get? On the other side, you get X minus IY. Now here it is nothing but A plus IB conjugate divided by C plus ID conjugate. Correct. So numerator is A minus IB and denominator is C minus ID. Can you see they are equal? So this is the first result. You can get this again. You can get this by rationalizing, but again you have to go back to this form. Okay, because you know what the result is. Going back to the form is not that difficult, but it's quite lengthy. Okay. Look at the second result. Now, because we know what is a conjugate, if you simply multiply the equations 1 and 2, you'll get your third result. Okay. Look at it. What is it? A plus IB into A minus IB. I'm just multiplying both sides. Okay. So it's C plus ID into C minus ID. On the other side, that is the right hand side, you have X plus IY into X minus IY. Fine. Can you see the numerator is nothing but A square plus B square, just multiplication. Denominator is C square plus D square. Other side you have X square plus Y square. This is also true because we just multiplied Z1 into Z1 bar, denominator Z2 into Z2 bar, and the other side, if you can see it, probably can take it Z3 into Z3 bar. So we already know that this is nothing but this modulus square. So what is the modulus of this? A square plus B square. So that root of A square plus B square whole square will be A square plus B square. What I want you to do is a small exercise. Right? So take the argan plane and I'll give you a point. Just plot the point. say it is the simple 3 plus 4i. So what is 3? Approximately this is 3 and this is 4. Okay. This is your point. 3 plus 4i. Let me just write it down. 3 plus 4i. Okay. What I want you to do is multiply this complex number. Let me name this complex number as well. Multiply this complex number with I. Okay. Multiply with I. Then plot the point. Some point you'll get, just plot it. Okay. Again, whatever now, just say, let me name it again. So it's easier. Okay. Say, the first point you get, suppose you name it as A. Okay. Again, multiply with I and plot it. Name that as B. Again, whatever point you get, multiply with I, name it as C. Please continue this process and tell me what you get. Okay. Just multiply with I and try to plot it. Okay. And tell me what you get. So it's very interesting that way, and it will get you a result also. Okay. So if you have tried, you can pause and try if you like. Okay. So if you try, so z into I, this is z, right? So 3 plus 4i into I, if I do, what do I get? Imagine part with 3i, this will be minus 4i. So if I look at it, minus 4, just approximately I'll put, this is 3. So this will be minus 4. Okay. Minus 4 and plus 3. So 3 is somewhere below. The point is minus 4 and plus 3. So this is nothing but A, right? This is nothing but A. Now again, I have to multiply A with I, which is nothing but minus 4 plus 3i into I, which is, say, minus 4i, and this would be minus 3. Now I want minus 3. They're just rough graphs, okay? I'm not drawing according to scale. I'm just trying to match it. So minus 4 I want. So minus 4 might be somewhere here. So this would be minus 3 maybe. So minus 3 minus 4. This is nothing but B. So again I'm trying to multiply B into I. So minus 3 into minus 4i into I. So what I'm getting, minus 3i, this is I square, so it's 4. So positive 4, x is positive 4, real part, and negative 3s. Now this is C. Now if you continue the process, this is very interesting. Look at it. C into I, what you are getting? 4 minus 3i into I. So you're going to get, say, 4i plus 3. Can you see that? We started here. Okay. You started here and you multiplied and came here. Okay. You multiplied and got this point. Again, you multiplied I, you got this point. When you multiplied I again, it came back to the same point, 3 plus 4i. Okay. There are different ways you can think about it. Okay. One is, you know what are I power 4s, correct? So we know what is I square, I cube, I power 4. I power 4 was equal to 1, right? So you might think, see, if I multiplied 4 i's, obviously I should go back to the same point. That's one way to look at it. Look at it the other way. Okay. When you multiply with I, when you come from Z to A, this is A, right? This is A, this is B, this is. What exactly happened? What is this angle? We get it as 90 degrees. Okay, you get it as 90 degrees. So why exactly it is moving by 90 degrees? What will happen if you multiply with minus I? Okay. These are the observations you need to make. Same exercise, start from the same point. You multiply with minus I and see what you get. You might guess the result, but you can try. You can try multiplying with minus I. So what will happen is, first you multiply, you will come to C. You'll go to B. You'll go to A. Then again you'll go back to C. Again, after 4 multiplication, you'll go back. Now the question is it true for any complex number? If I take any random complex number, say A plus I, Will that happen? Yes, it will. Because see what you are doing, you're multiplying with I once. Second time you're again multiplying with I again. Right? Third time you're multiplying with I again. And fourth time when you do I power 4 is nothing but 1. Or you can write it as I power 4. You can see that it will keep rotating like this. Right? Right? So any complex number you take and you just multiply this number, you're going back to the same point. I gave you an easy number like I, just to show you that these angles, what I is doing is making you rotate by an angle of 90 degrees. You take any complex number and multiply with I, it makes you rotate by 90 degrees. Okay. So you can think of if I multiply with minus 1 instead of I, if I multiply with minus 1, what will happen? Okay. Minus 1 is nothing but I square. So I just told you minus 1. Okay. So look at it. This is 3 plus 4i. This is the negative of it. Minus 3 minus 4i. Even in real numbers, when there were no complex number, whenever you multiply with a negative sign, it used to exactly change by 180 degrees, right? So look at it again here. What happens is it will change by 180 degrees. In real numbers, the problem was there was no number such that I multiply and get this 90 degrees. You can always calculate and do it, right? But there is no specific number like I in complex. So whenever I multiply I, right, I'll come across this change. Now there are more things to it. Why should I multiply with I, right? And how am I getting 90 degrees from it? Okay. Can I multiply with some number and get say some other angles like 30 degrees or 45 degrees, right? So that we are trying to figure out. Okay. So I can give you one more number, same result, say, same exercise. You have to do it repeatedly though. Okay. See, 3 plus 4i. Try to multiply this number. Instead of I now, take this number, say 1 plus I. Say 1 plus I is not good enough. So 1 plus I by okay. Try multiplying with this number and see what you're getting. Apart from this, you can even try say 2i just to see what is the difference. Okay. And see, multiply with 2i and see what are the results of it. If you do have done this exercise, what you will get is the points will move to the angle of 45 degrees. 45 degrees. Okay. If you have tried this, you will understand that the again points will move with the angle of 90 degrees itself because of I. Okay. But the magnitude will change. That means, so this was a complex number here. Again, it won't go to A, it will go to some higher number with the same angle, higher number. So you can't come back to the same complex number C. Okay. It will go some higher number. Again, to it will come higher. It will go higher. It will go somewhere here, right? Some bigger number. So because you are multiplying with the magnitude of 2 also, not only the same complex number. So what do you mean by multiplication? Whenever you're multiplying, what happens? Okay. So you've seen multiplication. So just to note it down, see Z1 into Z2. If I'm doing this product, Z1 into Z2, what exactly happens? Okay. Algebraically, let us see. We already know the result. So A1 in plus I1 B1, agreed, into A2 plus I2 B2. But simply multiply that. It is A1 A2 minus B1 B2. Fine. Plus I into what is the imaginary part? Say A1 B2 plus A2 B1. Agreed. So this is a normal multiplication when you multiply two complex numbers. If you look at the magnitude of these, right, magnitude of Z1, what is it? It is, say, square root of A1 A2 minus B1 B2 whole square plus A1 B2 plus A2 A1 whole square. A2 B1 whole square. Okay. Now, instead of taking magnitude for, I'll simply take the magnitude of Z1 and Z2. What am I getting? So you can see that it is root of A1 square plus B1 square into root of A2 square plus B2 square. Okay. So are these two the same? Okay. What I'm asking is, we can multiply the complex numbers and figure out the magnitude. Is it same as the product of the magnitude? That's what we're trying to figure out. And that will give you some idea why the graph is changing that way. Okay. So let us look at the product. So it is root of, say, A1 square into A2 square. This multiplying, so A1 square plus, say this should be B2. So B2 square. So it's into A1 square into B2 square plus, say, B1 square into A2 square plus B1 square into B2 square. Now the above result is not looking the same, but I think after a simple change or doing some calculations, let me just move this a bit down. So what the square root will change to? You can see that this is nothing but A1 square A2 square plus B1 square B2 square. And there is a 2AB term which is minus 2A1 A2 B1 B2. Similarly, there is A1 square B2 square plus A2 square B1 square plus 2A1 A2 B1 B2. You can see that these two terms are common and these two remaining terms, which are four terms, are equal, right? So when I multiply a complex number, the magnitude actually gets multiplied. So I can take the magnitude of them individually. So this is also an important result. So the magnitude of Z1 into Z2 is nothing but Z1 into Z. Now you can imagine what is happening when you multiply. First, I gave you I. The magnitude is 1. Correct? If, so let us take that example itself. So Z1, so the complex number is Z into I. So it was magnitude of Z into magnitude of I. Magnitude of I is 1 because it's root of 1. So it is nothing but magnitude of Z. So what was happening is this value was not changing much. Okay, the magnitude is nothing but length of the uh, distance from origin. Okay, the magnitude is nothing but the distance from origin. Correct. So that was not changing at all. You can see we multiplied it 4 times, so the magnitude remained the same. This is the reason, because when you multiply these complex numbers, you're getting the same magnitude. Okay. Now we can talk about in terms of angle what is happening. Okay, so actually when you multiply these complex numbers, the argument of the new complex numbers Z1 Z2, right? So this new complex number is nothing but the argument of Z1 plus argument of Z2. Sum of the angles. Now you can look in the same case what we did. So we said argument of Z into I. So this is nothing but argument of Z, whatever angle it was initially, plus argument of I. What is argument of I? I is nothing but a complex number 0 plus, sorry, yeah, 0 plus I. So tan inverse of, so I is 1 by 0. Technically, we can't take 1 by 0 and find out the values, correct? But we get an idea because what I is nothing but 90 degrees usually. Here it's 0. This is the imaginary part. 1 is here. Okay. So this is the angle we're talking about, 90 degrees. So argument of this is nothing but 90 degrees or tan inverse of infinity, what we're talking about here. Okay. So you get argument of Z plus pi by 2. Okay. So what you understand from this is when you multiply two complex numbers, what exactly is happening? The magnitude is nothing but the product of those complex numbers. Okay. And the argument is nothing but sum of the angles. So you can multiply any two, like I took I because it's very easy to see that this is changing by 90 degrees. Okay. If you had done this example, you would see that because of this, it's changing by 45 degrees. If you want, you can check how. Look at this. It is what? I plus, let me write down. So it's I plus, sorry, 1 plus I, right? So it's 1 by root 2 plus I by root. Fine. So if I multiply this to the complex number, whatever complex number, what should happen? That's what you figure out. So I gave this number specifically because look at the magnitude now. Magnitude is magnitude of z into magnitude of whatever number is there, right? So it is nothing but root of 1 by root 2 square plus 1 by root 2 square. Correct? So it is nothing but half plus half, which is nothing but magnitude of 1, which is nothing but magnitude of 7. So I gave a complex number in such a way that even though you multiply, the magnitude won't change. Okay, it will remain as it is. Now, look at the argument, what happens. The argument of the product is nothing but argument of the complex number, which is the angle already created by this complex number, plus argument of, say, I 1 by root 2 plus I by root 2. What is this? Tan inverse of y is also same, x is also same. This tan inverse of 1. We know tan inverse of 1 is nothing but pi by 4 or 45 degrees. So can you see that? Whichever next point you get will be the angle 45 degrees more. So for example, if you had multiplied this, so you would have got somewhere here, right? Somewhere here, this would be 45 degrees. Okay, this would have been 45 degrees, and you would have got one more point. Next point would have been A because it's going by 45 degree and it's not changing in magnitude, so it would have been A. So it's a very important observation. See, it's not usually what we do in our coordinate geometry, right? So here the representation can be well in terms of angles. We'll see that later what is the advantage of taking angles again when we talk about polar coordinates, right? And when we talk about Euler's theorem, right? Or Dumas theorem. Okay. In this problem, we have a figure. They have given one complex number W, right? They given one complex number W, and they have given a couple of points. We have tried to match them. Okay, we have tried to match them with these angles. So what is given? So we have to figure out what is W into I, what is W into minus I, so on. Okay, these are the angles given. First one, okay, I think this should be small w itself, not the capital one. The complex number is the same W, right? So W into I, you already know what happens. It changes by angle 90 degree. Now sometimes there's some confusion. So now 90 degree in which direction? Should it be in this direction or should it be in this direction? Okay. It's always in this direction, right? Okay. So the argument gets added. So this is your angle. So I'm multiplying a complex number with the argument of 90 degree. So it gets added 90 degrees to this. Now you can guess if I add 90 degrees, what I'm going to get. So it's nothing but F. This will be 90 degrees. So the question 1 is nothing but F. So shall we draw a math of a line like this? Okay. Question 1 is F. Next. Now the same problem with a negative I. If you still have a doubt, why should I take? You can use tan inverse formula also. Tan inverse of, sorry, this is not 1, this is 0. 0 minus 1. So minus 1 by 0. Okay. Fine. Again, we have a problem of dividing by 0. Okay. So what we do is we see where the point lies, right? So whenever it was I, it was here. This was the angle, right? The argument, correct? When it is minus I, it is here. Okay. So when it was I, it is 90 degrees because of this reason. Because 1 by 0 we can directly figure out. Because tan inverse, you can say infinity is pi by 2 and minus infinity is minus pi by 2. But it should be more accurate than that. You can't exactly say that is true. Okay. Easier way to figure out without any error is say, look at this, the angle made at I. Okay. So other values which is not coming as 1 by 0 or something, you can always use tan inverse formula. Okay. So minus I is here, so it is minus 90 degrees here. If you consider this as positive, this will be minus. Or you can say it's 270 degrees, but it's easier to talk about minus 90 degrees. That's why we use that. So minus 90 degrees, or this side is 90 degrees. So it should be an angle opposite to this F. So it should be this E. Okay. So question 2 should be E. Question 3, negative of this. I think this is very direct. So we know that this is nothing but multiple in complex numbers term. If you want to imagine, right? This is nothing but multiplying with 1. Sorry, multiplying with minus 1. Correct. So multiplying with minus 1 is nothing but rotating by 180 degrees. It doesn't matter which side you rotate now. You're going to get H. So question 3 is H. Question 4, negative of the conjugate of the complex. Okay. Now you can always see one other method. What is you can do is you can take these values and figure out. You know what is W from the graph because this is say 4 units and 2 units. You can do that also, but not really required. Okay, without that also you can complete the problem. So we're not going to use it. So what is minus W bar? So this is if this is W. Okay. First, let us find the fifth one instead of finding the sixth one, fourth one. First, let us find what happens here. If A plus IB is there, what we want is A minus IB. That means the real part should remain the same. That means this part should remain the same. And this part, if this was B, I want minus B. And you see that what point we are getting is A. So this is nothing, I can write it down here. This is W part. Or the fifth problem is nothing but A. Okay. Now you can guess. This was my problem. A minus IB. I'm multiplying with a minus sign or rotating with the angle 180 degrees. What is 180 degrees for this? It is angle B. So this is nothing but minus omega. So we can write what is F was. F was what? F was W into I and H was minus W. E was a W into minus I. Fine. Okay. So fourth one, let's match. Fourth one is B. Sixth one, W plus W bar. So what we are trying to do here, see, let us see if this is W, right? Let me write it down. This is W and this is W. So add what do I get? W plus W bar. I'm going to get twice the real part. So what is the real part of this? Isn't this the real part? This length up to D is the real part. But I need twice, so it should go up to L. So this will be our L. So whatever L is, this is nothing but say W plus W bar. The sixth one is L. And you would have guessed the logic. W minus W bar. If I do that, W minus W bar, I'm going to get 2IB. Now, this is your imaginary part already. I should get twice. It's not there in the graph at all. So let me just mark another point and name it as say. Is N there? No, N. And it's above the graph. Okay, it's double this length, whatever it is. O. Let me name it as O, and you have to map it to O. There's no answer for 7 in the current graph. Okay, so this is nothing but O. This is W minus W because it should be twice that length, not only that length. Okay, the imaginary part twice that length, and it's not there in the graph. This is the length, so it should be twice. Next, eighth one. Now you can see we know what is W plus W bar. It's twice the real part. But divided by 2, if I do, it is nothing but this D. Right? We already know this, so let's mark it D direction. Similarly, it is O. This entire sum is O. It's twice the imaginary part. Only the imaginary part is G. So ninth one would be G. Okay. 10th one is nothing but the reverse side, that is the negative of the ninth one. Okay. Again, you can use multiple logic. It is 180 degrees from this, so it should be here. So 10th one should be. All based on angles, very easy to figure out. So if you're thorough with this, you have understood most of how multiplication and angles work in complex numbers. Okay. The points are given here in this problem. So ABCD is a square. So we know a lot of information apart from this. We know that all the points, right, must be rotated by 90 degrees to get the coordinates, right? That's one of the hint. Second, I think simply by using the graph also you'll get the answer. But let's not try to use the graph and guess, okay? Because we already know what it should be. So D is 4 plus 3i. We have done the same experiment. So what should we see? So if I multiply D with I, that is rotated with 90 degrees, I should get C. That is nothing but 4 plus 3i into I. That is 4i minus. Same way, rotate C by I or 90 degrees. Multiply this with I to rotate by 90 degrees. So that minus 3i, say minus 4. A would be minus 4 minus 3i into I or minus 4i 3. Okay. So this would be all of your 4 options. Now, okay, the question is not finding A, B, C, and D, but everything related to A, B, C, and D, so you can directly write the answer. What is the real part of the complex number C? Real part is minus 3. Imaginary part is 4. What is the real part of complex number B? It is minus 4. What is the imaginary part of complex number B? Minus 3. What is the real part of complex number A? It's 3, and imaginary part is minus. These are the answers. Look at this problem. Set of all points Z in the complex plane which obey the following form. Now, what do you mean by modulus? We already discussed geometry wise also, right? If we know algebraic also, it is nothing but root of x square plus y square or root of e square plus b square. Let us look at the geometry part. It is nothing but the distance from the origin. Now, the distance from the origin, it's a variable point, remember, is 5. So, if I keep the distance from the origin constant, which is 5 units, and rotate, what am I going to get? It's a circle of radius 5. Can you see that? So, what I'm saying is here, the distance from the origin should be 5. So, there will be another point here, which is again 5. Similarly, if I keep on marking all the points, all you're going to get is a circle of radius 5. Fine. If you want to solve it algebraically, right, what do you mean by modulus? Nothing but root of x square plus y square, assuming your z is nothing but x plus I, right? Okay, is equal to 5. Can you see this? If you have seen this equation in circles, you know that this represents a circle with center at origin and radius 5. That will give you the same answer. Okay. With circle with radius 5. Okay, again, you have time to find the set of points which obey z plus 2 is equal to 1. Okay. Now look at this. It looks somewhat similar. This is nothing but z equal to 1. We had seen modulus of z equal to 5 and z equal to 1. They're totally different. Okay. This is nothing but a point, a single point, because z equal to 1 is nothing but a point where the real part is 1 and imaginary part is 0. Suppose the problem was the real part of z is equal to 1. That is a different question altogether, because here it says, this says, z, real part is 1, imaginary part is a variable which we don't know, which can be a straight line. Okay, it can be a straight line. So the imaginary part can vary, only real part is 1. But when we equate the complex number to a specific number, we are saying that the imaginary part is 0. When I say z equal to 1, that means imaginary part is 0. That means this represents only a single point, that is 1 comma 0. The set of all points z in the complex number which obey the following forms: z into z bar. Okay. So z into z bar, if you remember, what is this equal to? It's nothing but modulus of z whole square. Fine. Which is equal to 1. If you're saying modulus of square is equal to 1, what do you mean? Isn't it same as if I write down this modulus, let me just try to write down. This is x square plus y square is equal to 1. Can you see that? It's a circle. X square plus y square equal to 1 is nothing but a circle with the radius 1. Right? If you draw the circle whose radius is 1, okay, it's x square plus y. Center should be origin, obviously, 0, 0. Other way to look at it, does that mean that modulus of z is equal to 1? Right? If that is the case, that means what? That means the distance from the origin is equal to 1. I'm still going to get the same result. We have tried to find sum of the three angles in the figure. Okay. One of the method what you will do is find by units. Right? Yeah, this is correct. For P, probably you have to guess. There are 8 units here and 8 units here. That means what? Let me write down the points. Okay. Let me write down what is P. 8 real units and 8 imaginary. So this will be P. How? Just calculate. Because we can't use a protractor to get the answer. So only 1, 2, 3, 4, 5, 6, 7, 8. So each of these are units of 4. All are 4 squares. Therefore. Other way you could see it's a square, therefore this should be 45 degrees anyways. But let's just use complex numbers. Okay. So P we know. What is Q? What is Q? Similarly, real part is 8, imaginary part is 4. So real part is 8, imaginary part is 4. What is R? Real part increases now. Real part is 12. Imaginary part is 4. It is fine. Now look at it. If I want to find the argument of P, this is tan inverse of 8 by 8, which is nothing but tan inverse of 1, which is pi by 4. So I know that this angle is 45 degrees or pi by 4. Is okay. Now the problem arises if you use the same logic for Q. So tan inverse is 4 by 8 or tan inverse of half. We know sine inverse of half, cos inverse of half. We don't know the angle of tan inverse of half. We can't use calculators. Okay. So you have to figure out to find some other approach, right? Something else we could do to figure out what is that angle. The advantage here is they have asked you the sum of all the three angles, not the individual angles. Okay. Same way, if you try for argument of R, you are going to get the same result. It's going to be 4 by 12. Okay. So again, it is tan inverse of 1 by 3. If you're in 11th or 12th, you know more about inverse functions, right? You can use the formula tan inverse of A plus tan inverse of B. But that we don't know at this level. So we're not going to use that. Okay. What instead we can do is, do you know that if I multiply these two complex numbers, we're going to get this new complex number whose sum is nothing but the sum of the angles, right? So one way you could have done simply multiply all three without even finding the angles. That's what I said. You need not really find the angles, but because we already write this down, we would already know the angle, so why not try, right? If that is simpler. Now let us simply multiply these two because we know this angle of P. Let us multiply these two, get a new complex number, and see what that angle might be. Okay. So what we are going to do is Q into R. So 8 plus 4i into 12 plus 4i. 8 into 12, I'll keep it as it is. Let's not multiply unless we need to. Right? So now 4i into 4i, which is minus 16. Okay. Next is I into say 4 into 12. Again, there's one more I, 8 into 4. Agreed. 8 into 12, let's just multiply and keep now. 8 to 16. So 96 minus 16. This is 4 into 12 plus 8 into 4. So you can write 4 into 20 or 8. Can you see the complex number is nothing but 80 plus 80i? Now you would have guessed. Argument of QR is nothing but tan inverse of AP by 80, which is nothing but tan inverse of 1, which is nothing but pi by 4. So the angle made by P is pi by 4. Sum of these two angles is equal to pi by 4. So Sum of all the three angles is pi by 2 or 90 degrees.